When you look at physics over the last century, you hit a hard wall the moment the microscopic world collides with macroscopic gravity. General relativity perfectly maps the cosmos, and quantum field theory perfectly maps particles. But if you try to combine their mathematics to describe a black hole or the Big Bang, the equations break down and produce infinite, unusable nonsense. Einstein's framework of gravity is incredibly precise at the scale of stars and planets, but it is completely isolated from the quantum realm. Traditional attempts to fix this, like string theory or loop quantum gravity, start by assuming spacetime already exists and then try to chop it up into quantum pieces. The Information Manifold Model, or IMM, takes a different route. It asks a far more structural question. What if gravity isn't a fundamental force at all? Because the legacy models refuse to fit together, our map of reality remains entirely incomplete. To move forward, we have to look at new frameworks and decide exactly which theoretical trade-offs we are willing to make. The core premise of the IMM is that the four-dimensional universe we observe is a projection. It is a lower-dimensional shadow cast by a higher-dimensional informational manifold. Think of the geometry of projection. If you shine a light straight down onto a 3D sphere, a cone, and a cylinder, they all cast the exact same flat 2D circular shadow. From the shadow alone, you can never reconstruct the original object. The IMM argues that observation works exactly the same way. Vast amounts of informational states are irreducibly compressed, permanently losing data to create the single, definite outcomes we experience as physical reality. Under this model, gravity isn't a pulling force. It emerges as what the mathematics call a pushforward. It's simply what the underlying flow of information looks like after it survives the projection into our spacetime. To gain this mathematical alignment, you have to pay a steep conceptual price. You must abandon the assumption that the physical universe we walk around in is the true base of reality. Standard physics relies on the Einstein-Hilbert action simply because its math perfectly matches how we observe planets and stars behaving in the sky. It gives us incredibly accurate rules for how gravity works, but it never actually derives why the rules take that specific form. The action is essentially an empirical guess that happens to work. The IMM takes the opposite approach. It mathematically derives those exact same Einstein equations, showing they are stationary, fixed point of an underlying informational process. The mechanism forcing this is called a spectral-gap field. It acts like a dynamic regulator, decaying unstable configurations until only the stable, fixed-point geometry remains. Even the cosmological constant, a notorious fine-tuning problem in standard physics, emerges automatically in the IMM equations as the residual potential energy left at that stable minimum. Standard models observe the cosmos and dictate gravity's rules. The IMM derives the mechanics to show why those exact rules are mathematically unavoidable. Standard physics also struggles with time. It artificially inserts a timeline into space using a mathematical trick called Wick rotation, forcing time to behave differently from the three spatial dimensions. To explain why time only flows forward, physicists have to assume the universe started in a highly specific, flawlessly smooth state, like Roger Penrose's whale curvature hypothesis proposes. The IMM removes the need for special initial starting conditions entirely. It relies strictly on the geometry of projection. Because observation is a many-to-one projection, compressing many possible states into a single outcome, the volume of the past is strictly larger than the future. The data loss is geometric and irreversible. That bottleneck forces time to flow in one direction. That exact same projection dynamic drives a contraction flow, where any other timeline signature immediately decays. A Lorentzian signature, 3 dimensions of space, 1 of time, becomes the only mathematically stable structure left standing. This specific derivation does have a technical gap. It still relies on pending functional renormalization group analysis to formally prove the math holds up at every scale. But the setup means the arrow of time isn't treated as a random cosmological accident. It is an inevitable geometric consequence of observation. To test something like string theory, you have to probe the Planck scale. That requires building a particle accelerator roughly the size of a galaxy. The IMM operates on a much more accessible level. Its effects appear along measurable spectral gap gradients that scale with the expansion rate of our universe. This chart shows the structural growth of the cosmic web over time. Standard models predict one path, but the IMM predicts a highly specific power law deviation, an exponent of exactly 1.063, branching off from the standard curve. That deviation parameter is not a loose suggestion. It is the hard metric required by the math, serving as a direct pass or fail test for the model. We don't need a galaxy-sized collider to find it. Existing terrestrial observatories and large-scale structure surveys are collecting the exact data needed to check that curve right now. There is also a parallel test at the microscopic scale. Circuit QED experiments can look for the PIM-borne deviation, a specific measurable shift in the probabilities of quantum outcomes. The IMM demands immediate falsifiability. If the telescopes and quantum circuits do not detect these precise deviations, the entire framework collapses. The Information Manifold Model is not a finished magical answer to everything in physics. Adopting it comes with a steep structural cost. It accurately maps the Einstein equations and the arrow of time, but it explicitly admits its gaps. It cannot currently explain why spacetime has exactly 4 dimensions or why Newton's gravitational constant has its specific numerical value. Where legacy theories easily fit those constants to match observations, the IMM leaves them completely open as unsolved research directions. The heaviest requirement is the ontological leap. You must accept that physical reality is driven by a higher dimensional informational structure that you will never be able to directly observe. You are trading the comfort of a visible, 4-dimensional universe for a highly structured, mathematically rigorous shadow. If you are a pragmatic physicist, if your day job involves calculating satellite trajectories, engineering tolerances, or standard model cross-sections, you do not need this framework. Stick entirely to standard general relativity and quantum field theory. The IMM's deep structural layer provides absolutely no advantage for daily, practical calculations. But if you are a foundational theorist, and you are tired of untestable string dimensions and the massive fine-tuning problems of the cosmological constant, your calculus changes. Solving the core disconnect between the macro and micro universes requires diverging completely from the old legacy models. The IMM offers a clear path forward because it trades the untestable math of the Planck scale for structural integrity that can be measured today. Whether the information manifold model proves to be the final answer or not, it does exactly what a new theory should do. It pulls foundational physics out of abstract philosophy and puts it firmly back into the realm of testable science.